Anyways, yeah. Good evening, guys. So welcome to the tutorial. So there are some questions. Let's discuss one after other, and we'll go forward with what are the questions, what are the answers you can play. How do you know the answers or not? Then we'll discuss about them, how you can explain this thing. Okay, is it visible for you guys? Right. Then the first question you can look into it, that it's like a hydrogen sulfide is gas or liquid or solid? Hydrogen sulfide H2S. It's an intermediate question, by the way, right? It's a gas.
Yes.
And if you cool it down, is it going to be solid at any some temperatures? Liquid? Can it be a solid? Cool it down. If I cool it down, it should be.
Zero Kelvin can be.
No need of that temperature. Okay, helium itself will get into liquid in the like a 4 degree, 4 Kelvin or somewhere. Right. So now question going to be this way. So for example, if you look at the hydrogen sulfide at minus 16 degrees, that's going to be the solid. By the way, that temperature. Now, if you look into the packing of it, it's going to be like a close packing, which is going to be with like a hydrogen sulfide and minus 16 close packing structure with each molecule having 12 nearest neighbors. So I hope you know what you mean with nearest neighbors. Like if you look into it, what are the nearest ones which is available, right?
Sir, 1 minute.
So you have the 12 nearest neighbors, and there is no hydrogen bond even there. Okay, but why is the structure is different? And if you look into again hydrogen sulfide versus water, what's the difference? Is going to be the same angular shape, more or less they are same. However, ice is going to be a very different structure, which has a very strong hydrogen bond. But once you come to the HTS, you don't have such strong hydrogen bond, and the packing going to be significantly different, and so on. So, what are the reasons? One after other. Yeah.
The H2S is Divo compound.
HTS is Drivo. Okay. Anything more like in bonding side or any other perspective, like dipole moment, or let's look into like any other like a bonding side.
And H2S is HCP. Maybe.
Yeah. Okay.
Neighboring.
No, first let's look into like hydrogen bonding perspective, because the basic difference coming from the ice and H2S is coming from the hydrogen bond, and that's the typical reason they always like it needs a lower, significantly lower temperature, almost like 60 degrees lower to get it crystallized. Let's consider that way. So what happens with the hydrogen bonding side?
That's electronegative.
Okay. In other words, you can say it's like as a polarity, actually, more like a developmental polarity, because the electronegativity difference between the sulfur and hydrogen. Any idea of it? What is the sulfur electronegativity? दोनों के बीच, लेकिन सल्फर का कितना होता है कुछ याद है? Like, do you know that? How much is it? Yeah, it's 0.9 is the approximate you're talking about. But sulfur like almost how much is it? Approx 2.5.
ऑक्सीजन का 2.5 तो सजेस्ट नीचे अप्रॉक्स 0.5 का डिफरेंस जाता है 2.5
2.5. Usually you look into it like at least like you look into it, you have fluorine, below fluorine chloride, 4, 3, 2.5. 4, 3, 2.5. This is the rough way of at least like you can memorize this way. So it's a 2.5. Hydrogen, how much is it? Electronegativity? Any idea?
2.1
2.1 and 2.2. So the difference is literally 0.2. Right. But if, how about like water molecule? Oxygen, how much is the electronegativity?
3.4.
3.5 roughly. Okay. And oxygen again going to be 2.1. The difference is almost like 1.3. So the polarity is going to be significantly high in case of water, something like H2S, and that makes the hydrogen bond to be formed, and these are very strong. Okay, because of the significantly strong hydrogen bond in the ice, and you literally have a lot of like it will form a liquid even in the room temperatures and solid in case of solid actually. Like when they are making the solid, it forms a very strong bond. And literally, if you look into it, now how many hydrogen donors you have it and how many hydrogen acceptors you have it?
Two hydrogen donors.
Two hydrogen donors. How many acceptors?
Two
One,
of them.
one acceptor. Only one acceptor actually. But it can have it. If you take it to ice, how many hydrogen bonds it has? If you take into the ice, how many hydrogen bonds it can form per water molecule? It can form 4, right? But by the way, just now professor was mentioning about like as you increase the temperature, the ice volume reduces. What happens from the solid to liquid? Number of hydrogen bonds decreases from 4 to 2. Okay. Any other answers?
3 and 4.
Between 3 and 4. Okay.
3.4.
Usually it's a 3. Because usually let's say 3.5, somewhere in between, not even more than 3.5. So 3.5. So literally you are reducing, like if you look into this, you have a hydrogen bond over here. Sorry, let me put it this way. And so you have literally 4 hydrogen bonds in the solid. Right. Now you have the idea like it's a very polar and significantly that makes the compound to be gaseous. And if you look into it, like more or less, this will be even in the solid. In the case of like very high temperatures, is like a 0 degrees centigrade. Whereas if you go into like a water ice, it will be like H days is minus 60 degrees roughly. And now you look into it, hydrogen produces at minus 60 degrees centigrade in closed packed structure with each molecule having a 12 nearest neighbors. And there is no hydrogen bonding. As we know, the difference is like hardly 0.3 actually, not 0.9. It's a 0.3. Yes. And why the structure different from ice? I believe now you get the answer, or still you have questions over here. At least from the hydrogen bonding, it's gonna be like 4, but I need to look into the structure to find out.
It's only 4 for in ice.
4.
4 nearest neighbors.
Only 4.
So in contrast, for sulfur is 12.
Having
Yeah, it acts as a van der Waals,
It's not even hydrogen, it's a van der Waals.
close packed.
yeah.
Okay.
The contrast is from the electronegativity differences. Of course, this is was it gate score, gate question?
Actually.
Yeah.
Gate or IIT is one of these, I believe.
IIT, yeah.
Because they usually this first question usually we study in the intermediate actually. But yeah, we want to go a little further, so we'll start with the simple questions and then go further. Yeah. Then let's go into the next question. Can you give a reason why crystals of protein have a greater tendency to adopt high symmetric crystal structures? I think you have a rough idea of like different crystal systems, like triclinic, monoclinic, orthorhombic, and so and so. And whenever you have a systems, it always goes to the high symmetry system, which is like tetragonal or hexagonal or cubic, which are high symmetry, than do other organic molecules. So if you look into it, organic molecules do undergo crystallization more or less all the crystal systems, but preferably in the less symmetric, which is going to be triclinic, monoclinic, and so on. So, okay, but whenever you come to like proteins, it's always mostly into the high symmetry systems. Any reasons? Do you have any answers for this?
The non-covalent interaction presented.
Yeah, because of
Non-covalent interactions presented.
but organic molecules also do have the non-covalent interactions, right? You can do like
Number of non-covalent interactions more in case of Protein.
Protein. Okay, great.
Strong.
hydrogen bond equals a three peptide bond and form of the CO.
Hydrogen bonding.
So NH2
Try to put it in English because professor cannot understand a word of Hindi.
in protein, there exists peptide bond that is CONH2. So
Yes.
NH can form hydrogen bond.
Wonderful. Okay, but is it you can also observe similar hydrogen bond in the organic molecules also? If you take it like benzoic acid and you vacuum briefly, you have come across like
By stacking.
peptides doesn't have like paper stacking, by the way.
Yes.
DNA and nucleic acids have the paper stacking, not the peptides, which is going to be amino acids. 21 amino acids we have. So, yeah. Any questions? Any suggestions or answers? For example, let's look into the energy perspective. I think I might have told you in the lecture, especially for MSc first years actually. Whenever you have a freedom, a compound, if you give a freedom to a compound, does it like to go into the higher symmetry system or lower symmetry system, and why? High symmetry. Why? Lower in energy. So they always have a significantly lower in energy. And now let's go forward into the proteins. Is it like if they are polypeptides, and you have if you look into proteins, actually they're hugely solvated, especially water. Now, and is it like is there any rigidity like a phenyl rings, or do we have any of such things? No, right? Peptides are like very flexible. CH2, NH2, literally they are very flexible. And now you have a solvent molecule in these things. When you like to crystallize it, does it have a more tendency to the high symmetry or low symmetry? High symmetry, right? Because now there is no rigidity. For example, if you look into it previously, like organic molecules, most of the times, you have aromatic systems and they are very rigid sometimes actually. But in case of peptides, your rigidity goes down.
Here we can say that organic molecules are discrete because discreteness is closely linked to the rigidity. And they are very big, they are not having molecularity. They are 3D. 3D directionality is 3. Molecularity going to be 0. They are not treated as discrete. So they are flexible. At the end of the day, they're gonna show a lot of greater number of weak interactions, which fall them to the region of symmetry.
They like to exactly. That's like exactly. Since they are less rigidity, more of like more easy to bend and they can adjust accordingly. Especially they are solvated, so they always like to go to the symmetry. Okay. By the way, now I have an answer. Like if I have a question, if I remove the solvent, does it go to the again like high symmetry or low symmetry? Or it can go both. I am removing the solvent. Previously, it's a hugely water containing systems. Okay. And now I am removing the solvent. Does it go into the high symmetric or low symmetric?
Shall go to high symmetry, even more extent. I think this stabilization.
More stabilization, okay.
Yeah,
but
stabilization means more towards the symmetry they are going now.
Yeah, but actually, when you remove the solvent, your rigidity comes in picture because your hands are like your 3D structure, right? They doesn't like to move. I think they usually go into the lower symmetries because their flexibility get reduced and their freedom of expression gonna be reduced. Maybe you can help me out. Is it correct, or maybe I'm going through different route?
No. Again, it says that it has got peptides. It's a highly flexible one. It's trying to minimize, when it tries to crystallize. Of course, it tries to form like globular kind of, a spherical type of thing. It tries to crystallize. Whenever you have something like this, it tends to crystallize in high symmetry.
High symmetry. But if I remove the solvent and
the solvent will be occupying the empty space. There's no void space there. There's a lot of water, in fact, in all the protein crystal structures.
yes,
It's squeezed out, but it's still floating in the
water molecule. Yeah. But now I have a question also here, like follow along with our answer. If I'm reducing the amount of solvent and we are pushing the molecule to be crystallizing it, is it can go into the higher or lower symmetries?
Just to, I mean, well, it can go to anything, because it's a polymorphic,
No, it's gonna be
Yeah.
polymorphic. Okay. Yeah, but there is a tendency.
Energy minimization is important, under what condition it's crystallized.
But actually, there is a now previously is high possibility it can go into the higher symmetries. But once you're removing it, the flexibility or like possibility of amount of water present there is going to be reduced. That's what I was reading through it, saying okay, once you start removing it, the floating ability of the protein reduces. Floating ability, because floating means you have to have a solvent, which is the water, right? And if the solvent is reduced, now it has a more tendency compared to previously go to the lower symmetries.
If we apply the same logic to the organic
Mm-hmm.
compounds, then
Mhm.
if we reduce the solvent by equal to them,
They are usually already crystallized in the lower symmetries most of the times, except you have a very good symmetrical molecules.
consider now that when the solvent is removed, the solvent clamps like on the organic. But hydration and enthalpy is also complete.
Hmm?
Hydration and enthalpy factors. Due to more solvation, there is larger hydration and enthalpy.
Yes, but like when you talk about the organic molecules and hydration, yes, solution. In other words, let's put it like solution. Solution will be there, but as you remove the solvent, whenever they crystallize, very little solvent left over. Usually, most of the compounds are crystallized with a limited amount of solvent, unlike proteins, because the interactions are somehow they stabilize itself and they form a less solvated. I think that could be one of the reason. If you look into most of the compounds, organic compounds or metal organic compounds, they are in the lower triclinic. Most of the crystals, if you really look into the survey of, if you really survey the crystals reported so far, that most of the compounds are crystallized in monoclinic. Highest, I think it's a space group of highest is a P. It's a P2 P2 upon
C.
P2 upon C.
Yeah. It's talking about 35% of
All the
the
crystals.
structures reported in CCD belongs to
C2 upon C.
Yes, P2 upon C.
Yeah, so that's why like they always go into the lower symmetries because of like various reasons. Yeah. So any question over here? Like, could you able to follow this question now, or could you able to understand it? Okay. Yeah. Then go to the next lecture. Next slide. Next point, which is going to be the most phenols exhibit OH oxygen hydrogen bonding in the solid state. However, if you look at it, OH can also form a OH pi interaction. Okay, so very few compounds show the OH pi bonding in this question. Give reasons for this observation. So now, if you look at it, phenol, like phenol, right? Now, phenol can form hydrogen bond. Let's look into this one perspective. I think it, meanwhile, it can also form with the pyrite. Which one is more dominant and why? Most of them show me which one is more dominant among these two, which is going to be number one and OH number one.
OHO is most dominant.
OH is more dominant. Why not this?
Because OHO bond strength is more as compared to OH pi interaction.
Okay, any reason?
Because of polarity difference.
Polarity difference.
Yes. I think we discussed the answer, in fact, in the class. You have to have steric interns or something to prevent this kind of strong thing. Then it goes to 6 volts.
Okay. Okay. So can you scroll down? Scroll up. Little more. Yeah. Let's go into the question number 4, which is going to be crystal structure of amino phenols. Okay. Crystal amino phenols have both OH ends and OH bonds. Okay. And generally, which of these hydrogen bond type is stronger? There are two bonds. Hold on a minute. Let's complete this. Okay. And then which of the bond is stronger and why? would amino alcohols expected to show both these types or anything little bit predominant, anything dominant among these actually? What is, there are two bonds now, right? So one is gonna be NH O and OH N, and you have a possibility of both. For example, you can now phenols, right? Let's put in like OH over here. That it can have a possibility of this one can interact like a next one. The next molecule can this can also this is also possible. Okay, as well as you can also have a OHN and NH again, like NH gonna be OH. I hope you can follow me here. This is gonna be NH2 here. This is gonna be 1 and this is gonna be 2 because there are two types now, OHN and NH2. Which one is more dominant and why? Is there any actually predominance of one over the other? That's another question for the three types. OHN.
Is the polarity
Okay, again the polarity difference and OHN is more predominant over NH2. Okay, so more or less I think is it also covered again?
Also, both should be present here.
Both should be present, but it's a bit predominant actually. OHN. OHN is a little bit predominant over this one, but it's a little bit actually. It's not a significant difference in energy because polarity wise, oxygen nitrogen is decently closer. Okay, but like still this is going to be high. Dominance actually. Yeah. The next one going to be this is going to be more like the drawing side. Maybe you can draw it and let's discuss about it. So 3-cyano, 3-cyano ethynyl benzene. Okay, give the experimental structure of the. Okay, sketch the possible crystal structure patterns of 3-cyano, 3-cyano ethynyl benzene, and given the experimental structure of 4-cyano isomers are in this chapter, which like I think we have covered. I think professor has covered in the yesterday's lecture. Assume CH, N, and cyanide interactions will be written. So this is the non-covalent interactions, which is like the CHN. Okay. With cyanide. Okay. Now you have a cyanide which has a covalent non-covalent interaction with. So here bonded to. Now you have this. Try to draw the structure of how it's going to be in the 3-dimensional, or at least in 2-dimensional. You can try it out. First of all, is it a planar or non-planar molecule? Plane. So it's going to be forming sheets. Going to be forming sheets. Try to draw the structure.
It will form a C. This number will vary. I think. It may be 3.
Draw that's it, like you draw it patient, don't rush. And I have given that because it's not enough space. You should look into the you look into the angle something so that you can understand how many molecules can come in one if you want to set your link or sheet or somewhere. Because right, why are you really struggling? Is it? But this makes you much comfortable. You don't realize it or what? You can also take off. Mhm. It can also improve one more, I think. That is that stock is there. Or the rest. What's the angle between this one? 120. 120, right? 120. So 120 means normally marks you're supposed to expect. How many marks you could expect in a year?
5.
No.
5, 6. Any other question? Is there any other option? 6. 6. 6 or
6.
Benzene is a
Uh-huh.
different. But it's a cyclohexane type.
second separately.
If it's cyclized, right?
Yeah.
Otherwise,
Then it would be the.
Possibility.
Zigzag or linear or any other structures can go.
Zigzag, linear and free.
So now I hope you can you got the question or answer more or less. 1, 2, 3. Right, it is gonna be here, and it's gonna be the cyanide. So this is gonna be like a next part gonna be the other side of it. Same gonna come. Could you able to follow me, Suraj? Yes. So this is a cyclic form. Non-cyclic form or linear form also can form. You can also get that. Next one question gonna be like question number 6. Sketch the crystal structure of 1:1 molecular complex of CBF4 and urotropine. How many of you know urotropine structure?
H2 6 and 4.
H2
6 and 4.
H2 6
and 4.
and 4. Okay. Structure. Is that right? Right. Now you have to crystallize it 1:1 of. It's a crystal structure of 1:1 CBr4 urotropin, CBr4 and the urotropin. You may assume that this structure based on N and bromine has interactions. Okay. Can you predict the crystal structure of this system for a binary count? Do you have any? Can you sketch it out, or is there any possibility? It's going to be
given
difficult.
is wrong. What the base which is given is wrong.
Is it?
It has to be tetrahedral. Also tetrahedral. What is one is wrong. Yeah, it has to be tetrahedral. They occupy, both are tetrahedral. See, look at this figure. I didn't even now I noticed.
Literally, you have a this can form. If you really look at it, it's a tetrahedral form. Actually, 4 nodes are there, right? And now you also have it.
And here,
Again, it's gonna be tetrahedral.
And so. Yes.
Yeah.
Now they are going to be together.
diamondoids
Done.
based on N halogen interaction.
Yes.
NCl, NBr.
Here. So you look at it diamondoid, right? So you have diamond. Every carbon is 4 bonded. Similarly, this also can form 4 bonds. This can also form 4 bonds. It's going to be diamondoid structure.
Just now I saw this. It's funny though, but yesterday I copied it and put it there.
I was also kind of like looking at it, how it is to be drawn this way. Next question gonna be. Did you get the idea?
No, 7 next question.
Yeah, okay. I thought you have a question on here. Right. Next one will be 7. The compound has a nitro ethynyl and 4 nitro ethynyl benzene. Okay, instead of ethynyl, just now we drawn it, we have it. So instead of cyanide, we have nitro group, and we have 4 cyano ethynyl benzene, and have a similar structures. Can you suggest the reasons? So let me draw the structures of both the compounds. Is this molecule? Now there are 2 molecules now, and they form almost very similar structure. Okay, any reason?
Actually remains in a linear like.
Okay, great. Why?
But I think these 2 groups occupy almost same space.
You see here, this is going to be like different shape of us. How can they come into the same one?
Again, the answer given is wrong. It's given, he has given the wrong one.
8th question will be.
Okay, come in.
They shouldn't have.
I think let me help. What he has given is wrong. Yeah.
Any suggestions? Any reasons you can talk about? Actually,
Yes.
No.
so symptom we talk,
Is it known?
Yeah, that.
Yes.
If it is known, then it should have the same structure.
They almost have the same symptom. Similar symptom, not the same.
But if it is not given, then we can't say about this. Na?
Hmm?
But if it is not given, but if
If
it
it
is
is not given, what?
then we can't say about the structure.
But if you remember, like last lecture actually, she said that they were discussing about the syntons and tectons. If you look into synton, this is one of the synton and syntons are very famous. So they are both are linear, isn't it?
What if we hydrogen, if the same thing happens for both oxygen, the two different molecules come and attach, they should branching, it should show branching something.
Yes, it could be another polymorph. Yes, I agree with. What do you mean? I understand your question. So you have one molecule over here.
Another,
So this will come over here, this will come over here.
yes,
But usually this bond gonna be strong.
No, I mean, you don't have many acceptor, you have two acceptors and one donor. It has to be bifurcated. So it has to form the way pros are drawn. It should form exactly the same way.
Unless you are
Bifurcated, we have more donor, right? Only one acceptor. No, two acceptors. So it's bifurcated.
Unless you have any.
Yeah, that's a one. That's correct. So just
also we can say that will not connect. If we consider,
Bulkness means it's like they are linear and simple, right?
if we connect the two, if we follow about bifurcation, and then we connect the two, then there will be.
But stoichiometry, I mean, look at the stoichiometry. If it is 1:1, it's the same compound, right?
Yes. So you have one acceptor, one donor. By chance, if you have this one, maybe whatever you're speaking about could be happening.
1:2 case.
Yeah, I mean, when you have something like this, then I'm not sure. There will be some non-bonded.
Now you have two.
Oh, should be there.
Yes.
You can see here one donor and two acceptors, so they have to share. But here you have two donors, two acceptors. If you want it, maybe that time it can.
Now, yes.
Okay. The crystal structure of 4-halobenzonitrides, halogen can be, it consists of linear array of molecules joined in a halogen nitrogen synthon. All the structures are layered, most of them. Sketch a diagram of a non-centrosymmetric crystal structure for this family and the polymer centrosymmetric structures. I think you have briefly studied about the SHG, and before that you might have studied a bit of non-centrosymmetries, right? And if you have a molecule of like 4-halobenzonitrides, try to draw them such a way that they use a non-centrosymmetry systems, and especially it's a linear array of systems, linear array of molecules if you want to take it. Can you draw that? Some structures, some kind of arrays where they are forming non-centrosymmetric structures. Okay, let me draw it for you guys briefly. Take the molecule. Can it form, or can you be able to draw the structure with a non-centrosymmetry? Does it have centrosymmetry first of all? No. It's non-centrosymmetric. Can I draw some array of atoms or array of molecules? It will be non-centrosymmetric. Not always will form a non-centrosymmetric. It can form centrosymmetric if you arrange them in properly.
From CL, if we add some same form, then. From CL, well, exercise, where engine attached, if we add some same form, that from, yeah, I think it will.
Try to draw something, then we'll present it. You can draw is like take an arrow like that and it is easy to draw. Don't try to completely draw the whole structure.
Just a halonitrile, right? So how would you draw? I think the answer was given in the thing also. The lecture notes.
It's a linear compound, by the way. Arrange them in an non-cytosymmetric fashion. That's it.
I mean, it also says that join with the halo nitrogens in the, that's a halogen bond. So
So it is bent. Benting can be combined linear. Let's see earlier.
no, only between halogens.
Yes, yes.
So, for example, you can now you have it right.
That is also possible. Yes.
Okay.
Yes.
Now let's draw this one in the other opposite side next time. Does it have cytosymmetry?
Yes.
You have a cytosymmetry. Then how do you get non-cytosymmetric if you want to?
Same line.
Hmm?
In the same body.
I don't-
Has to weigh the answer.
Then it also should come this way. Does it have any cytosymmetry?
No.
No.
And that's again you are looking at it here. This is like, for example, you look at it from nitrile and halogen, there is a bond. But in case of this, it's gonna be again also have a like halogen bond, halogen bond. Is that clear? Again, it has to be linear because if you look at it, the molecule is linear, and the interaction is gonna be again with the X over here, nitrogen. It will be linear arranged. It cannot be bent. It cannot be zigzag. That's what you're pointing out, right? Bent.
That is fine.
Okay. Any questions over here?
After the hydrogen, that bonding,
Mm-hmm.
it form linear chain type.
Yes.
How does linear chain type?
They are arranged. They can be arranged that way, right?
On what basis?
Sir, in this arrangement, is there pi interaction is also there?
Hey, absolutely right. Pipeline interactions also can go forward.
Stacking.
Then
Pipeline interactions can follow, and hydrogen bonding interactions are there, and it can be further stabilized by like arrangements also, right? Is that right? Is that fine now? Obviously, like you have an aromatic system. Don't miss it. Is it planar or not planar system? By the way, it's a planar. So easy can stack. Easy to stack. Okay. Again, we are putting in the 2D space. Like 2D arrangement. That's what we are looking at. Next, we can gonna be it's a trigonal heat structure based on NHO hydrogen bonding that one can expect from a symmetrical molecule like cyanuric acid. I hope you know the structure of cyanuric acid. If you don't remember, I'll draw it for you. It is an unsolved problem today. So as it to why this trigonal structure is not adopted by the compound. Although it can form a very nice structure, but somehow it is not adopted. Any reason? First of all, cyanuric acid. How many of you remember the structure? C3, H3, N3.
Like benzene.
we have this
Like benzene.
Is it?
carbon
Alternative.
alternative
And OH.
Oh, exactly. Other structure, there's a combination can easily draw it. You know very good organic chemistry, right? And now you're
Carbon, nitrogen alternative will be there, the forming are
carbon, nitrogen, carbon, nitrogen, carbon, nitrogen. So you're literally C3 and 3 is over. Now H3 and O3. H you can come back like about, can it have NO bond? Not really easy, so usually it goes. And you have a H, 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 and you have a pendulum.
Five. OH will be in the place of C double bond.
Okay,
So double bond.
Double bond OH.
So that double after will be C double bond will be replaced by COH.
hold on, hold on. Sorry, it doesn't have double bond, but this is now right. Yes, we are right. But it does have a keto enol. It will have keto enol. It's gonna be like a OH. Then this will go down here. This will go down here. In such cases, you have like a double bond here. That's what. Yeah, I remember this way actually. It has a keto enol isomerism. Now, can you draw structures which can form like some kind of cyclic structures? Does it have any hydrogen bonds? Can it form?
Yes.
By the way, is it a planar or non-planar again?
Planar.
Planar.
Then polar sp2
Yes.
Nitrogen is sp2 or sp3?
It is SP2.
because of tautomering. So it is sp2 evidence.
Yeah, learn pair actually. But it's supposed to
will go in tautomerism.
exactly. That's the reason you need to be plane.
Maybe let me comment that. Okay. What I'll do, okay, you have this, right? So you've got OH, this can form. So let's assume that this is, I mean, well, you can write similar one, which you can, where you can have something like this with the double bond here. It should have O here. And it should have H here. If it is H, it should be N. And then you can draw something like this, okay? So this is a kinate, here this goes. Three. So okay, extended is a trigonal. 3. Okay, so 3. Okay, so this is formed, this is symptom. So same thing on this side, same thing on this side. So it's a trigonal. So she has given a second draw.
Yeah, I was searching like how it is made.
Yeah.
Because according to me, it's gonna be honeycomb like structure.
So yeah, this one. So it's a trigonal. But actually, it doesn't form. That's what he says. Why? It's supposed to be like this, right?
Yes.
I think see the validity of this. I don't want to use this. Questions. Okay, why it doesn't form?
what diagonal pair bond angle should be 120, but here I think due to steric content, it will not remain 120.
It can be distorted. That's not, it can very easily be distorted because it forms, this forms cyclic structure complementary that it leads to stability. Let's think about it. Okay, if it forms, there are 2 or 3 reasons you can talk about why it doesn't form. But one reason, well, maybe you'll know only next week. No, tomorrow, not next week. Tomorrow. Because when we talk about polymorphism, the other one is if you try to do it this way, it creates a lot of empty space. Packing will be a problem. Empty space, it forms a sheet, and the other sheet, maybe, I don't know how it goes. That kind of packing may be a problem. And second reason is, depending on the solvent that you use, it may give rise to different polymorphic modification, different phases, polymer phases. That's another reason. That's why whatever you think, higher symmetry, when you try to crystallize, it won't crystallize in high symmetry. It always crystallizes in lower symmetry. Only in the case of metal oxides or metal sulfides, 1:1, they're all spherical in nature. They tend to crystallize in high symmetry. We have inorganic and organic. Although you have symmetry associated with the molecules, they don't, because there are a lot of other structures that are stable. Like they are also stable. Okay, so that leads to the formation. It's a kinetic product. Usually that's what we call. So I think packing is one of the problem here. When you try to pack something like this, it will create a big void. It's going to be big hexagon.
Yes.
So
Honeycomb structure. It's going to be honeycomb actually.
yeah, honeycomb.
It's going to form a honeycomb structure.
So you'll have a lot of empty space in the middle.
Why we don't talk about the packing efficiency when we need to have higher porosity?
Yeah, but I don't think such things are known in the case of hydrogen bonded compound. But now for coughs, people are using it for coughs and H coughs in hops. There they're trying to make. I don't think this is known. Even if maybe you may be able to.
It may form rhodoxins and cationins to very large extent.
Yeah, but in principle you can try it, but in practice, that's what they say.
Solid state.
They haven't observed this one in practice. Okay, they try, but although you can try this one is the most stable, trigonal, because based on a lot of reasons.
It's going to be like literally like if you can do the structure, going to be this one actually.
Yeah, it forms honeycomb. Yeah.
And whatever you see here node is there,
This
node, and the hydrogen bonds are this way. And you literally have a lot of empty space here.
Yeah, it's a lot of empty space.
And it's not usually, it's like if you look into the energy, the thermodynamic perspective, it's like empty space is very far below. Which means like it's higher energy system. Unless we are forced like COP, that's what like the professor was mentioning, or MOP, even MOP are there is a kind of where we have empty space. But there is no option other than going there. That's where they go. But in case of hydrogen bonds, these are like flexible bonds, or these are non-covalent. In case of the bonds, they are coordination bond or the covering. But if you look into this, it's a hydrogen bond. Compared to the covering and coordination, it's weaker in bond. So it always will try to go, not to go here.
in MOFs are the covalent bonds.
Coordination bonds. MOP.
Coordination bonds are also
It's a kind of covalent, you can say that. It's a strong.
crystal engineering and these type of
Additional kind of covalent
weaker
bond.
interaction we study.
What is it? What says? I just missed it. What did it say?
In MOFs, etc., the structures, we don't study about the weaker interaction, weaker than the bonds.
In the case of MOFs, no. Only covalent bonds, only coordinate bonds.
Coordination
Bonds are, very important because it can be broken very easily.
It's a
That's the only
kinetic.
reason.
It's not the node, and it's a kinetic if you come to the coordination bonds.
Yes, yes.
And also, as you see here, you say that why can't it, be,
But when you have solvent kicks in inside, they will start forming hydrogen bonds. If you have water, or if you have anything, they will distort the whole structure, forming hydrogen bonds. Unlike MOF is all coordinate bonds, and then other solvents can get into empty. It's not possible in this case. It can't even be interpenetrated because there are other structures that are lower energy that will be formed instead of this kind of thing.
Could able to follow, right? You could able to, yeah. Next one going to be identify the supramolecular synthesis and DNA base pairs. AD? How many bonds? AD? A to D? A? AD has a two bonds and GC? Three bonds.
It follows crystal engineering.
So do you want to draw or is it like fine and let's move on?
It's known, Google it, they will know.
Then next question gonna be, this is gonna be very interesting. Scroll down, Aditya, scroll up actually. Yeah. Hold on, yeah. AG forms two different coordination polymers, okay, with a preferred background. And let's consider charge neutralization apparent by the non-coordinating anion in each case. So which means silver is not bound to any anion. And coordination polymer has a 1:1 and 1:2 geometries. In both the cases, all the nitrogen sites are all the sites in the ligand are coordinated by the metal atom. Given the AG can have a variable coordination geometries such as like linear, trigonal, and tetrahedral. Sketches the possible network structures for both the compounds. So you have a silver and you have BPY, 4,4-BPY, and now you have two geometries, two stoichiometric 1:1 and 1:2. And your silver can have a linear, trigonal, planar, or even you can take it up to T shape also will be top because silver do follow form a T shape. Okay, linear, trigonal, or tetrahedral. Try to draw the structures what it could form. Do you understand what I mean? What other question means another word? Interesting. Okay.
In the 1:1 case.
Yes, sir.
In case of 1:1 ratio.
Only linear shape size.
Let's put it this one as a stick. Okay, let's put this in. Okay, it forms a linear strike. Gonna be 1:1. How about 1:2? Tetrahedral. Okay. What is the structure gonna be look like? Diamondoid. Why?
Base pair is different.
How about you? What can form a silver and tetrahedral of silver as well as a 1:1 like BPY as a linear link. How about like trigonals? We look into the trigonals.
Same like seat like this benzene test. For trigonal.
Trigonals. What is the structure of this?
Honeycomb.
Honeycomb. Can form honeycomb. You took it, take it a silver over here, pillar over here. You have a BPY over here. It can form a honeycomb, but is it really forms? The ratio will be different.
It will not.
1:1 actually. 0.5.
Sharing 3, that means half each. So
Yeah.
For a
1:2.
tree shape, like ladder type, it's 1:2. Ladder type. There's a two linear ones joined by one BP. Yeah. That will be
It could also be extended further.
It will be extended. That's where I put it.
here also 1.5. That's also 1.5. Yeah, 1.5. It's also only tetrahedral is, yeah. Because 3 times half is, 1.5. That's another,
Only tetrahedral it can be 1.2.
yeah, tetrahedral is 1:2. Yeah.
Yes, sir. that is
Tetrahedral.
Tetrahedral is 1:2. Sorry, yeah, this one is 1.5.
Yes.
So the gain one BP will be vertical.
Sir, if it is
Half each, right? So half each. So 3 times half is,
Again, it's going to be.
yeah, again, it's same thing as the X, yeah. Yes, exactly.
One structure was that ladder and again ladder and that was rounded. Why?
Planar is not,
No.
only diamond die, yeah, diamond die.
In ladder is also silver has 4 bonds of four entity rounded.
Where?
One ladder is the base and one ladder in they bounded.
Yeah, you have to think about the geometry of silver.
You can say the silver gonna be having a 4 numbers again.
It cannot have square planar.
It's not just planar. The one piece.
It's, some weird geometry.
Sir,
Yeah, some
It
weird
will
geometry.
be this way.
if we increase the ratio as 1:3, then it will form the structure. or not?
If it is 1:3, I don't know, maybe one will be non-bounded.
Yes.
Yeah, one side will be non-bounded.
And those things are not. It cannot take it any further. Its maximum is a tetrahedral. Silver cannot go further. So if you get one more, it will not react.
Yeah, 2, 3, and 4. I mean, if you have a chelate, then you may say somewhere, 5, but usually not. If you have acetate or something, if you say,
Huh.
you will not be nice.
But in any case, like if BPA is going to be in excess, even if you kill it, you are reducing the amount of coordination sites. Obviously, it will be non-bounded. Even if you kill it. And the last question.
I didn't know that.
But they had given it.
Scroll down.
Start in the text and you're getting the diamond topology. Changing the metal ion. Oh, okay. And the ligand. Oh, yeah. I mean, it's today's, you guys should know.
Actually, crystal structure of zinc cyanide. This is in the text. I think it's
I give a lot of examples anyway. Yeah.
Given this text. You are required to maintain the diamond topology of the structure after change the metal ion and ligand. Suggest 4 coordination polymers that can satisfy these conditions. You got already one here, I think. Okay. Anything more? Any other suggestions? Do you understand what I mean, right? You got one suggestion here. You can. And BPY can in the tetrahedral more 1:2 geometry, 1:2 of metal and linker. It will give a diamond dot.
Yeah, that is okay, yeah, it's an answer.
Yeah. And any other structures?
Cadmium.
Cadmium.
Cadmium with cyanide.
Yeah, cyanide should also be replaced. I mean, any linear, any spacer, linear, spacer.
Don't make it such a simple, right?
Why not extend the pyridine? Or pyrazine. Or BPE.
We can use still be
Still can it coordinate?
One side is nitrogen. No, still being is both sides is just phenyl. Right?
Phenol. Can it coordinate?
that type of condition that both sides we use that pyridine and inside there is a double bond.
Double one. Yeah, that's what called as a BPE actually.
BPE, yeah.
You're saying copper one?
In copper one like every year pick the Kz +1 oxidation +1 coordination number. Similarly, if we took copper in +1, then will it form
Yeah.
It can form.
Copper one is a very good suggestion.
Yes.
The problem is copper ones are very air sensitive.
It will immediately oxide.
Yeah, that's a very good, it is possible. We have done, you can very easily form them.
In electronic principle, we have studied that copper, AgAu, plus
Suggestion.
Yes, the carbon forms a tetrahedral. That's what sir is. Any other suggestions?
Beryllium one positive complex.
Gold usually forms a lane. Yeah.
What is it? What?
Beryllium one positive.
Gold forms.
First of all, beryllium is very toxic. Okay, I mean, beryllium, yeah, maybe you can use it.
Yeah.
Not many
You need to.
MOFs are known with beryllium because of this problem.
This nitrogen related.
And the main thing.
Any transition?
Also do with cadmium, then cadmium also carbon.
What it is?
Usually silver, zinc.
That zinc cyanide is also poisonous.
I know. But beryllium, yeah, it's very small. I don't know. Yeah, you're right. But usually, no, MOFs, of course, they studied, but I don't know, not many have, I don't know, any MOFs have been known with beryllium. That's what I'm saying.
Some of the compounds with beryllium plus one oxidation state have been
No,
more recently.
But mark guys, it does it.
I don't know. I haven't heard. That's why.
Barium, yes, I saw a lot.
Persian blue, they have used, although it's poisonous, but not beryllium. Beryllium may be quite expensive, but I don't know. Maybe more toxic, I think.
And there was one suggestion here, urotropin with the
Gold.
gold. Urotropin is a tetrahedral and gold can bond the nitrogen and nitrogen.
Good suggestion. Yeah.
So you are always looking at like metal, right?
Yeah, gold, silver. Yeah, gold, silver instead of gold. Silver may be better. Yes, silver is no. Silver is urotropin. Yeah.
So you put it like silver or
Silver. But gold is not possible.
Gold
Because it doesn't, I don't see any gold with two nitrogen bonded to it. On one side, it should be carbon or some.
It can form.
Huh?
But I think it can form.
You can form.
Okay, in principle, yeah. But silver, is known. I've seen. Silver is known.
The reason for the silver to make such thing.
Huh?
The reason for the silver to make such thing and gold is not any explanation.
I mean, usually gold doesn't, say, according to me, on one side, I've worked on gold, for some time, but on one side you can put nitrogen related ligands, the other side is carbon, then it is linear. It is possible. And I don't see any other way of including, cyanide is the one on both sides you can put in and it forms, but I haven't seen gold in MOFs. But silver, yes. It forms linear geometry, but gold one is supposed to form. In principle, you can, if you write, if you write it, I have to give you full marks, but in reality, that's a different thing. Gold one forms linear geometry, so, and by all means, you can write. Yeah.
Any other? So now you look into like two configurations, You have a silver, it's in tetrahedral geometry. Then you have to have a linear linker. Okay, which is born in from the both the directions. Other one possibility is like you have a tetrahedral linker.
With lineage.
It will be a linear coordination geometry. Such as silver, copper one, you may take it. Silver one. Now, if you want to take it like gold, in case. So here you have tetrahedral you can. And you can also get both tetrahedrals by the way. So it's going to be again like silver tetrahedral also can give you the same.
Iron sp complex can it be?
Iron sp2. Iron is in tetrahedral, like it's a node which can has like a case it can form. But the bond next to iron has to have a nitrogen sulfur bond, preferably nitrogen iron bond.
For some reason, not many iron containing MOFs are known. We don't know, like there are a lot of metals missing in MOFs. I don't know, mostly cobalt, manganese, nickel. You can incorporate very easily, but not many iron. Even chromium, very rare. Very rare.
Why?
Both the bonds are tetrahedral.
Yeah, with sulfur, yeah. The sulfur, again, it's a protein model, right? Yeah,
That's what he was saying.
yeah.
System.
It was what is.
Yeah, CO is known. They see carbon can be replaced with any linear cyanide or something.
Something later can take it. Any other notes of tetrahedral?
Wait a minute. This example comes under the category of outer electron transfer mechanism.
That's reactivity. Okay, what is
This
it?
because
Okay.
I have just made the presentation on this. Now, how here we are talking about the interaction and H bondings.
There's a reactivity versus your stable compound you're talking about. You're not talking about reactivity. You're forming a compound.
For coordination bond. And here are the coordination. It's a
Iron can form a bond. You can, for example, if you want to take it. Yes. That right. That's the simplest link I can take it immediately. Can go some to this. No, absolutely. You talking about this node or this one?
this.
This one is stable actually. Kinetically, yes, you are right. Kinetically it's labile, but you can still make it. Whatever the complexes you have seen today, most of the compounds, they are mostly metal with a carboxylic acid. And like thermodynamically very, but kinetically, yes, you need a lot of moisture into it, the stability, you are right, they are level. And that's how, actually, that's one of the challenge in the market, but people are solving it with a different examples. I think that's all for the examples. I hope some.
I'll try to send it tonight for next tomorrow.
Okay then guys.